So we'll give you a biased introduction to algebraic numbers, maybe with a focus on group theory. So it won't be comprehensive, but it gives you some interesting phenomena, I hope. So let's call it algebraic numbers for group theories. But these invariants, they come from algebraic topology, and well, what are they? They are, first of all, numbers, like the usual Betty numbers. So there's a sequence of numbers, these Betty numbers, for every group gamma, and also for every space. There are these algebraic numbers of the space X. And they share some, well, similar properties with the Betty numbers, but there's one difference at least. They are a priori real numbers. And it will be part of the second or third lecture to actually see what is the possible range of these numbers. So these are the algebraic numbers that I want to talk about. And we will approach the definition very slowly. Maybe before I start, I give you like 4 or 5 facts about these algebraic numbers so that you see most basic properties. First of all, what is the relation between these two things? There is something for groups and there is something for spaces, so that's similar. There are Betty numbers of groups and there are Betty numbers of spaces, and the relationship between the two was actually in the last part of Uri's lecture, in the classifying space part. So so we all know, you can know. Yeah. So I assume you all know what the classifying space of a group is. No, let me say you some words about the classifying space. So this is somehow now the last part of Uri's lecture, and it's intended to explain how you get from an invariant of a space to an invariant of a group. It's very general. If you have a homotopy invariant of spaces, you get an isomorphism invariant of groups, and here is how it goes. Classifying spaces. So what you do here is you start with a group, discrete group, there's no topology on the group, and you associate to this group a space that's usually called B gamma. And well, there is a functorial construction of this space. Functorial means that if you have homomorphism between groups, it gives you continuous map between these spaces, but that's not relevant to us. What I offer is a description of this space that's unique up to homotopy. So there is a space B gamma, and what's really unique about it is the homotopy type of this space. So not the actual homomorphism type, just the homotopy type. So to each group we associate a certain homotopy type of space called B gamma, the classifying space. And a nice way to describe this space, or to give the defining property of the space, is actually to look at its universal cover. So the universal cover of B gamma is usually denoted by E gamma. And I will give you the defining property of E gamma. And then B gamma will be just the quotient. Okay. Well, that's definition and theorem if you want. let gamma be a group. And then there is a topological space. And let me put in bracket, actually you can choose a very nice space. Equivariant CW complex, we'll say, comment on this in a second, but there is a topological space with a free gamma action on it, and this topological space is contractible. And it's also unique up to homotopy. Two such spaces are equivariantly homotopy equivalent. This means you have a map from one to the other, and this map has a homotopy inverse, and both the map and its homotopy inverse are gamma equivariant. Okay, so the gamma equivariant homotopy type is unique, uniquely determined if you assume that the space is contractible and has a free and any such model we call E gamma, or we denote by E gamma. And if we have E gamma, V gamma is just defined as the gamma quotient of E gamma. Okay, so this is the space. So the theorem in this part here is the fact that it's unique up to equivariant homotopy equivalence, and well, it's not so hard to show, but I will do it somehow outside the lecture. But assuming that now we have a general scheme of associating to a homotopy invariant of spaces, an isomorphism invariant of groups. So whenever you have a homotopy invariant, yeah, but I want to first state this and then I'll give you an example. So this homotopy invariant, I mean, could be anything. It could be, I don't know, numerical, like in this case that you associate a number, or you can also have an invariant that associates a Euclidean group, like homology. Whatever you have, I don't know, Euclidean groups, or elements in R, or whatever, then you get an isomorphism invariant of groups. And again, this is just because well, the fact that this E gamma is unique up to equivariant homotopy is equivalent to saying that so defined as B gamma is unique up to homotopy. So whatever example of B gamma I take, since this is a homotopy invariant, I get here a well-defined define numbers, say, in this case for a group, and this is how you go from spaces to groups. Okay, so this is how you define L2 numbers of groups if you have if you have defined L2 numbers of spaces, which we will do in the course of this lecture. But okay, so this is the general scheme of what Uri was about to say, but now let me give you an example of these classifying spaces. So, examples, classifying spaces. So whenever you have a space such that its universal cover is contractible, this space is V gamma for its fundamental group gamma. Let me mention this first. So if the universal cover, usually denoted by x tilde, of X is contractible, then this X is just EP1X, and X itself is E pi 1X, just because X tilde has, of course, a free action of its fundamental group, the deck transformations, and contractible, I just assume. And we have many examples of that. So for example, if you have a hyperbolic manifold, okay, if you have a hyperbolic manifold, we know by standard theorems in differential geometry that its universal cover is actually isometric to Hn, to the hyperbolic n space. But in particular, the hyperbolic n space, just as a topological space, is the same as R to the n, so it's contractible. So E of, or B of a fundamental group of a hyperbolic manifold is just the hyperbolic manifold itself. So this is the case e.g., or this is the case if X is the Riemannian manifold admitting, more generally, not hyperbolic metric, but admitting Riemannian metric of lambda-strip curvature. So this is a huge class of examples. So for example, also contained in this class is the example of the integers. So if you take, if you look for a model of the classifying space of the integers, then you see the circle has fundamental group Z, its universal cover is R, it's contractible, so it falls in this class of examples. So this is S1, and its universal cover R is EZ. Okay? But, okay, so there are also examples that are coming from other sources. If you look, for example, at put this a bit on here. So for example, if you take the group C modulo 2, so finite group now, easiest example, non-trivial example of a finite group, then this group acts freely on spheres, okay, antipole map. So now what happens is that, of course, the sphere is not contractible, but somehow the homotopy groups of the sphere, they vanish up to degree n. So in degree n, it's Z. So the nth homotopy group of Sn is the integers. somehow, if you increase the n, then you increase what's called the connectivity somehow. Then you can, by increasing the n, you can somehow assume that homotopy groups to the degree 1000 are trivial. And when you look at these sequence of spheres with these group actions, you can somehow put them into a compatible system, and you see that C2 acts on S infinity, which you can think of as a co-limit, or in this case you can think of as a kind of limit, like S1 sits in S2 as the equator, and so on and so forth. And if you do this, then you end up actually with a space that has no homotopy groups, and it's contractible. It has a free C2 action, so this is the classifying space of the universal cover, and if you take the quotient, then this will be the co-limit of the various projective spaces sitting in each other, so this is R infinity. So that's an example that's somehow not manifold like the examples on the right hand side here. It's a different sort of example. And okay, and maybe I stop here with this short digression to classifying spaces, and come back now to these Betty numbers. Mysterious because they're infinite dimensional, or?
Well, I mean, how did I build these two objects? How did I know that this was the right thing to do? I mean,
well, somehow you know it because, okay, first of all, there is no guaranteed scheme that leads you to the classifying space. And it's not guaranteed at all that you have a nice model. For most groups, we just know by general theorems that there is some space that can be very ugly. And it might be very complicated because the homology of B gamma is what's called the group homology, and it's somewhat notoriously hard to compute. But in this example, of course, the first thing you look for are some spaces with a nice action of the group given. And Sn is such an example. And then, well, it's just this observation that somehow Sn is very high connected, so it has vanishing homotopy groups up to a certain degree, n-1, and then you push it off to infinity. So maybe in that example it's not so surprising, but in general it's like very often it's a theorem that you can publish if you found a nice model of a classified space of the group. Yeah. All right. Now, let me go back to the Betty numbers. They are also notoriously hard to compute, and very often it's actually not the question of the exact value that we're interested in, because we have no chance of computing it. Very often the question is it 0 or not? So this is somehow the most important thing. And somehow to give you a definition of what it means that the ith Betty number vanishes or not, this is much easier than giving you the definition of the actual value. And we'll start with that. So we'll give you the meaning of this number to vanish. But maybe, okay, there are many motivations to look at this. Also, if you're a group theorist, not a topologist, there are many motivations to look at these numbers. And I just want to give you one theorem, which is arbitrarily taken, and there are many, that give you the motivation why you're interested in the vanishing of an Betty number or not. It's not so old, theorem by Lackenby. And it says that if your group is finitely presented, and finish the sentence and then I'll tell you. With positive spectrum number. Then gamma is large. Okay, so let me explain your meaning. I won't write it down because it's just an appetizer. I'm not going into this theorem now. It's just to make you interested from a group theoretic point of view. So, what is residually finite? A group is residually finite if there is a sequence of subgroups of finite index such that the intersection of all of them is trivial. So you can exhaust it by finite index subgroups, normal subgroups.
In the indexes.
And now if I say P finite, I just want that the quotients are P groups. So the index of all these finite index subgroups are P powers. And okay, somehow you want this theorem actually without the P, but this is the theorem that's available.
And what is the meaning of gamma is large? What this means?
Yes, what is the meaning of the conclusion here? So gamma is large means that up to going to a finite index subgroup of gamma, it subjects onto a free group, a non-abelian free group. So there is some subgroup of finite index, might not be the group itself, that subjects onto a non-abelian free group. This is the meaning. So it's a nice structure theorem about the group, given that the first alphabetic number is greater than 0.
And this of course means that the finite index subgroup subjects to any group you want.
Yes. Yes. It also means that if you have a surjection onto a free group, it splits. It also implies that the free group sits inside gamma 0 as a free group. So in particular, you see immediately that gamma 0 and therefore gamma cannot be amendable. So there are many things you can deduce right away. And also you see that somehow the positivity of this alphabetic number immediately puts you heavy restrictions onto the structure of the groups. So it's somehow, it's the case that the alphabetic numbers very often vanish. And if they don't, usually has restrictive consequences. Okay, so now let me define the vanishing, also approach the vanishing, what it means of the alphabetic numbers. So this alphabetic number of a space X is some sort of dimension, or let me put it in quotation mark, is a dimension, but it has to be defined. Of the so-called L2 cohomology of the universal cover. Okay, so this is not cohomology like Uri defined it. I will say in a minute what it is. It's some modification of what Uri introduced, but it's some sort of cohomology of the universal cover of the space. In particular, this is a space that has an action of the fundamental group, and surely this action also is there on the cohomology level, so there is not just a leading group here, there's also a leading group with a gamma action, and associated to such an object with a gamma action, there is a sort of dimension that has to be defined, but this will be the definition. But whatever this dimension is, it will turn out that under certain conditions, certainly satisfied if X is complex, CW complex, that this is 0 if and only if this gadget here is 0. So provided, let's say, if X is a compact CW complex, and therefore I don't have to define the dimension right away. will only define you this L2 cohomology, and then you will know what the vanishing means of the L2 eddy number. Okay, so what is L2 cohomology? So, as I said, in this example there should be tilde here. In this example, this is not only a space, it is a space endowed with an action, maybe the action of the fundamental group. But the definition of this L2 cohomology does not use the gamma action. So the L2 cohomology will give you the definition for, I don't know, the CW complex, just any. It's only if we go to the dimension part that we will utilize this gamma action on this project. So what is L2 cohomology? First, let me remind you, I'm not sure you did not say what cohomology is, right? You just reminded of homology. Okay, so let's say you look at the CW complex. And in this business it will be usually infinitely many cells. And then we saw, you can also, I mean, Uri talked more about simplicial complexes. You can also think of a simplicial complex and the simplicial chain complex. So there was the simplicial chain complex or cellular chain complex, what you prefer, I don't care. So this was this complex here. Maybe this is a bit misleading with the x, and here's the x tilde. Let me call it y. The y will be the x tilde later on. But the homology of this complex of abelian groups is the homology, but you can also look at the cohomology, and this is what I would like to do. And this is just done by dualizing this complex. Just dualize this complex, and as Uri said, that if you have a simplicial complex or CW complex, then this guy here is just the free abelian group, and it's the free abelian group on the set of n cells in Y if you have a CW complex, or it's the free abelian group on the set of n simplices if you have a simplicial complex. But whatever it is a free abelian group. So you can also think of this abelian group here. I mean, maps from a free abelian group to R is the same as giving a value to each basis element. So this is the same as just maps from, I don't know, n cells to R. Okay? So this is the cochain complex, and the homology of this complex is the cohomology. So hopefully this is also just a reminder for you. And for the L2 cohomology, we now look at a subcomplex of this complex. Okay, so we take a chain complex that sits inside this complex. And we do this by looking at maps from the n cells to R with a certain additional property. Namely, we require that the map from n cells to R is square summable. Just meaning that if you sum up the squares of the values of all n cells, then it should be a finite sum. Okay? And maybe I choose a notation now for this. This is somehow noted like that. So if I sum over all these n cells, it should be finite. And did it again, sorry. And this sits inside this guy. And not only as an abelian group, but the differentials that you have, they restrict to this subcomplex. It's really a subcomplex. And the homology of the subcomplex, it's almost this. But there's another decoration that I have to explain. Okay? So definition. So I will take the homology of this complex. So usual notation, if you take the homology for cochain complex, you write the I up there. So you have this definition. And now what is the bar? Yeah, let me motivate what's coming now. So if you look at the square summable maps from n cells to R, then this is of course just L2 of the set of n cells. So it's a Hilbert space. It's a natural way, it's a Hilbert space, and it has a preferred Hilbert basis, namely the set of n cells. Now, if you take homology of this complex of Hilbert spaces, it's not a Hilbert space anymore, because what might happen is that the differentials here, they are bound continuous maps, but it might happen that the image of the differential is not closed. So you divide out by a non-closed subspace, and what you end up with certainly has some sort of topology, the quotient topology, but it will not be Hausdorff if the subspace you divide out is not closed. So in order to get Hilbert spaces again, what you do is you take kernel divided not by the image but by the closure of the image with respect to this topology coming from the Hilbert space structure. And then this is this object here, what's called the L2 homology. Okay, so this is basically the same, but it's now kernel of, I don't know.
Maybe you can say that you take the pairs of the boundaries inside the kernel.
Say again?
Take the pair of the boundaries inside the kernel.
The pair?
Pair. Perpendicular.
Ah, okay, yeah. I will, it's actually what I come next. Now I will just give you a way to compute this, and it will involve harmonic cochains, and we will also look at a concrete example, and I think then exactly what Uri just said will turn out. Okay. All right. So let's do it now. So now I want to give you a tool to actually compute this. And as I said, this guy here, it is a Hilbert space. So somehow, when I say compute, I mean if it's non-zero, it will be infinite dimensional in most cases. So the cases that are interesting are the cases where Y is a non-compact CW complex, which here corresponds to the fact that the universal cover of this compact CW complex is infinite. This means that the fundamental group is infinite. So somehow for this theory to be interesting, you need some non-compact Y here, because if Y would be compact, then the square summable functions, I mean this would be finitely generated free abelian group, then it's just the same, and this guy is just the usual. But somehow in the interesting cases, you will have an actual non-finite dimensional Hilbert space, and then computing just means deciding whether it's zero or not, somehow. I mean, two Hilbert spaces of the sink. If they're infinite dimensional, they're infinite dimensional. There's not much more you can say at this point. Only later, when the group action comes into play, we can get more interesting information out of it. But now it's about deciding whether this guy is zero or not.
Can you say once more the closure of the image?
So, the definition here is, this object here is a complex of Hilbert spaces.
Yes.
And cohomology or cohomology, because I talk of co-chain complexes, kernel divided by image of the differential before. And now, due to the fact that the image of the differential might not be closed as a subspace in the Hilbert space,
Yeah.
I just take the same definition but with kernel divided by the closure of the image.
Okay.
And then this is my definition of this.
Okay.
And if I have a Hilbert space and I divide out a closed subspace, I again get a Hilbert space structure of this. So it will be a Hilbert space. And as Uri said, the Hilbert space structure can explicitly described by saying this is just the orthogonal complement of the image inside the kernel. When I say it like that, it's clear about what is the Hilbert space structure.
Okay.
This is what it was. Okay. So here's a tool for doing some computation. So let's look at this again. So we have the differential here. And common convention is not to put the degree in the notation of the differential, because you make certainly mistakes. So I will call them all D, but it's the differential in the correct degree.
These are like upper and
Yes, these are like upper. Exactly. Was it correct there? Yes. Yeah, thanks.
Using the metric to raise the
Okay, and now you can look at the Laplace operator in this simplicial or cellular setting. So the Laplace operator, you have it in every degree, and it is defined maybe not surprisingly as d star, d plus d star d. So d is a bounded operator in our setting, d star is the adjoint operator between the Hilbert spaces, and so d is the map, you go d star back, so it's an endomorphism of this, and here the same, you first d star and then d, it's again an endomorphism, the sum of these is delta is the Laplace operator. And now there is a nice description of the L2 cohomology in terms of this Laplace operator. Namely, if you look at the kernel of the Laplace operator, maybe now I actually put a degree, delta I, this is isomorphic to this L2 cohomology. So somehow it's often nicer to check whether the Laplace operator has a kernel rather than to compute this quotient here. That's why it's very useful to have this. Let's first think a second about this statement. It's very easy. So as Uri said, this guy here is just by definition it's kernel divided by closure of image of the correct differential. Closure, I guess. But another way to say this is that this is somehow the orthogonal complement of the closure. Okay, somehow I tend to write the closure like this. Maybe write it like that. It's the orthogonal complement of the image inside the kernel. Okay, the complement inside the kernel. And you know somehow basic Hilbert space theory that an element is in the complement of the closure of the image, or it's also in the complement of the image of the operator, if and only if it is in the kernel of the joint operator. Okay? So an element is inside here if, first of all, this element is in the kernel of D star, but since this is an orthogonal complement inside the kernel of D, it's also in the kernel of D. So what I'm saying is that we actually prove that this is the same as the kernel of D intersected with the kernel of D star. And of course, the D is this D here, and D star is this to here. Okay, again, let me repeat it once more. An element is in the complement of this image, and complement now in the whole space, if and only if it's in the kernel of D star. But since I'm taking the complement inside the kernel, this thing is actually the same as the kernel of D intersected with the kernel of D star. So this was all easy. Now we have to check that the kernel of the Laplace operator is the same as the intersection of the kernel of D and the kernel of D star. But one inclusion is certainly easy. If you have an element that vanishes under D and under D star, then just from looking at this formula, it certainly lies in the kernel of delta, right? So now, what about the other inclusion? You have an element that is 0 under the delta. Why is it in the intersection of these kernels? Well, okay, so this is some continuation of the proof that if delta of x is 0, then certainly delta of x, scalar product with x, is 0. But now, write the scalar product like this. Now using the adjoint, you bring D on this side, and you have that this is the norm of D star x as the norm of dx. And therefore, both have to be 0, and therefore x lies in the intersection of the kernels. Okay, so we actually proved this little fact here. And now we want to use it in examples. And by the way, so if an element lies in the kernel, if a cochain lies in the kernel of delta, we say this cochain is harmonic, by usual convention. So we want to look for harmonic cochains, but before we do that, we should now look at a concrete example. I mean, how do you compute this D star? Okay, so let's look at an example. And the easiest examples are where we have one-dimensional CW complexes. So if you have one-dimensional CW complexes, these are just graphs. And so we only somehow have cochains in degree 0 and 1. And take an example by one-dimensional CW complex, which just means this is a graph. And now let's look at what happens here. If you look at the, we only have one differential. And what is it concretely? Okay, so if you have this f here, or here's somehow a graph, some of the compute homology, you put orientations on the edges and so on. And now the D does the following. If you have, so what is df? df is now an L2 function on the set of edges, oriented edges. And this is the function E goes to f e plus minus f e minus. disoriented edge, then this endpoint will be E plus, and this will be E minus, or vice versa, whatever your convention is, and this is the differential. So now, let's compute the Laplace operator. We have two Laplace operators, we have one here and one here, and to compute the Laplace operator, we have to compute the adjoint of D. So what is the adjoint of D? Let's actually compute it. Okay, so the adjoint of D is given by the defining properties, of course, this. So let's start with this. If we have an L2 function on the vertices, this is the f, and G is an L2 function on the edges, then the scalar product is, well, if you sum over all the edges, again, edges are just one cells in my CW complex, and you do E of f E times GE. So I guess I started with real vector spaces. Maybe at some point I want to have complex. But okay, the way I defined it, it was all with real Hilbert spaces. If you do this whole thing with complex, then you would have a conjugation here. Now let's don't. So let's write it up. This is the sum over all E of f E plus minus f E minus times GE, and you bring it in such a form so that we can see the D star and just rewrite it a little bit, because on this side, this is a scalar product of a function on on vertices with another function on vertices. So somehow I want to write this sum over the edges as a sum over the vertices to see what D star is. And it's easily done. This is the same as summing over all the vertices. And then I have to sum over all the edges. Now I'm confused.
Starting and ending.
Yes, but somehow, okay. Yeah, sorry, others. Here I have the endings. And then I should probably also have the GE here, right? Okay. So what do I see? I see that the D star G of edge here should be I sum over all the this is V. So if I take this as D star G and take this scalar product with F, then I get
Shouldn't there
this
be
sum
a
here.
factor of 2.5? Because in the sum over edges, you count every edge once. Down in the sum over vertices, don't you sum there every vertex? Every edge twice? Kind
No,
of for
because I
incoming and
I have one orientation on the edges, so it's not that I count every edge twice with this orientation and the other. I just somehow to compute this, like I do in cellular homology, I orient my graph and then I have one orientation on each edge. So I think this is this should be the correct one. Okay.
Incoming minus the outcome.
If I
The two things are that
Flow
you
one
have
to
the
the
same vertex twice, but it's not the same edge connected. Vertex. I mean,
it's like in this graph,
Yeah.
if I have this, I don't have this. It's,
sometimes
Sometimes-
sometimes the same
I know.
vertex is the edge and the head.
I
but
know.
It's not the same. It's a tail and a head, but it's not the same edge and G. So
Yes. Yes, but sometimes there are different conventions and they count twice. I know, but in this case, as you set it up, it's this.
So it's incoming flow minus the outgoing.
Right. So d star G is 0 if every vertex the incoming flow is well, incoming flow defined as the sum of all values of
Is the
edges.
sign correct?
I think so.
Surely,
Okay, so it's supposed to
it
be.
is surely correct as it's written.
Okay. Yes.
I mean, just think of it as like
final-
an adding indicator function, right? That's always the easiest way to do these things.
Okay, so what does it mean now? So now let's look at examples, okay?
Will you tell us what the Laplacian is?
Yes, yes.
Well, the Laplacian in the one-dimensional case, if we look at the Laplacian in degree 0, it's just d followed by d star, and the Laplacian in degree 1, since there is no d on this side, is just d star followed by d. And but what we will actually use is in the example that comes now is the description of this group here as the intersection of the kernel of d and the kernel of d star. But now let's look at two examples that are
No,
qualitative.
but just as an alternative, as a nice matrix representation. Right. The Laplacian.
Well, it's if it's just an infinite graph, it's like it's an operator on an infinite dimensional Hilbert space, so it's described by an infinite matrix.
Yes, that kind of.
But kind of nice, kind of an infinite incidence matrix. Yes.
I think it's like 1
Whereas
minus.
it's on the diagonals minus the sum of all.
Yeah.
So let's look at the
So
concrete example.
Yeah, right.
up to again.
Yeah, there's degrees. You have the degree of each vertex sitting there, rather than just, if it's not, if not all vertices have the same number of vectors.
Let's look at these examples. Okay, so let's look at the real line. Choose orientation again. So the real line is the infinite graph. That's pictured here. And what about h0 of this? Let's call it L for line. Well, this is just the kernel of D. You don't need a Laplacian for that. That's very easy. It's just the kernel of D. There is no image there is no differential from before. So it's just the kernel of D. But looking at the kernel of D, what does it mean that f is in the kernel? Well, it means that if you have an edge and how do you say adjacent? Yeah, adjacent edge, then they have the same value. But this means here it's constant. All these values have to be the same. Okay, so f, our L2 function on the vertices, is just on every vertex you have a number, and all these numbers have to be the same if this function is in the kernel. But since these functions are also L2 functions, the value has to be 0. Otherwise it would not be square summable. So this is just 0, and actually this is a phenomenon that now you see for any infinite connected graph. You can do the same thing. If the graph is connected, the value has always be the same by this reasoning, and if it's infinite, the L2 function just forces the thing to be 0. But what about the H1? Well, we know that it is kernel of D homotopy intersected with kernel of D star, but this D would be the differential from one chains or from degree 1 to degree 2, but in degree 2 there is nothing. This is just a one-dimensional space. So this is just the kernel of D star. And the D star is now an operator from C1 to C0, and happily we just computed what it is. It's this formula there. And as Tobias said, I mean, it just means that, well, if you have an element in here, it is a L2 function on the edges, so each edge has a label, but if you have a vertex, then the incoming edge has the same label as the outcoming edge. If it's in the kernel of D star, this just again means that the values on each edge has to be the same. Since it's L2, it has to be 0. So we just computed the complete L2 cohomology of this one-dimensional infinite graph, and it completely vanishes. Okay. You might say, okay, but if I look at usual, just a second, you might say, okay, if you look at usual cohomology, we expect nothing interesting to happen since this is a contractible object. But wait a second. It's not the case that this L2 cohomology is a homotopy invariant on spaces. And we will see this in the next example. In the next example, we will look also at a contractible space, but we will have something non-vanishing in H1. You had a question?
So my remark is that, but the fact that the kernel of D star 0 is not something that, I mean, this is not generally true for graphs, right?
No, not in the next example.
So unlike, yeah.
The next example is an example where we have something in H1 and it's also one-dimensional. You have to stop me, I don't have the time.
Does not.
That's exactly what our.
Oh, okay.
So maybe give the next example as an exercise.
No.
You will solve.
No, I want to do this. It's somehow too important to do it as an
No, but
exercise.
you will do it. But let people
Give
think
him
over the break about it.
Yes, exactly. So the example is, of course, look at a tree. Look at I don't know, a regular tree, infinite tree, and show that the first L2 cohomology is non-zero. So for this, you have to come up with a harmonic 1 cochain, or since it's one-dimensional, what is the same, you have to come up with an L2 function on the set of edges of the tree, such that D star of it is 0. So such that every incoming flow at each vertex is equal to the outcoming flow, and it has to be a square sample. So it's not so hard actually. So solution after the exercise. But maybe I want to add one comment, then I don't have to say this later. What I said before, usually in algebraic topology you define homology as a functor on topological spaces. This means that also every continuous map induces homomorphisms between these homology groups. So this is a bit different here. I define here an object called the L2 cohomology, but it is not a functor. And the reason for this is the following. If you have a map, say from an infinite CW complex, infinite simplicial complex, that maps to, I don't know, to a finite one, and that just maps infinitely many simplices to the same simplex, you easily see that this does in general not induce a map in this L2 cohomology, because you might have somehow a code chain with a non-zero value on that one cell, and now you pull it back, and infinitely many cells are mapped onto this cell. This just means that on the level of code chain, you get a code chain that has the same value at infinitely many cells. So it can't be square summable unless it's 0, of course. So it's not a functor on spaces. You need some properness on the maps that you consider to get some functoriality. So there is some functoriality here. We'll tell you later after the break, but it's not just for any continuous map.